So welcome to another series of our game theory seminar. Thank you for the people that are present online and also the people that are present here with us at Rabat, at Moroccan Center of Game Theory. We have a big pleasure to have today Edith Elkind. She is giving an amazing lecture in the PhD program. And so Edith did his PhD in Princeton, then she was postdoc in Liverpool, Warwick, Jerusalem, before being in Singapore as assistant professor, then associate professor in Singapore, before joining Oxford University, where she was professor until this year. Now she's a professor at Northwestern University. She's one of the very important specialists in cooperative game, voting, social choice. So what is called as computational social choice. She organized many conferences like EC, AMAS, and ICHCAI, I think also. So all the big conferences in computer science related to these topics. So it's a big pleasure to have her here, and we are very happy to collaborate with her, and I hope this will be for a long period of time. So now it's the floor for you, Edith, and thank you.
Thanks, Rida, for a very kind introduction. So keeping track of my biography is a non-trivial challenge, and well done. You miss Southampton? Well, people do. Okay, so this is based on a kind of recent paper with my students Sonia Kreutsch and Isaac Robinson. So I used to be at Oxford till 4 months ago. So Sonia and Isaac both stayed back at Oxford, right? And I'm at Northwestern, and that explains the purple background of my slide. So purple is our color, right? And these 5 figures below, I'm going to explain during the talk. I'm not sure what happened to this one. It's not supposed to be turned over, but later you'll see slides where it's shown properly, and you'll see what that refers to. So what I want to talk about is participatory budgeting. Participatory budgeting, I don't know if it's something that happens here in Morocco. Rida, you would know. It doesn't? No. Not yet. I think if Rida stays here for 10 more years, it will, but for the moment it doesn't. Okay, so in participatory budgeting is a way to allocate some amount of funding, typically funding by local municipalities, based on the wishes of the residents of the neighborhood. So typically there would be a set of projects, right? And these would be like neighborhood improvement projects. So these are all examples of actual participatory budgeting projects, creating a new children's playground, improving the conditions in an animal shelter, investing money in firefighter training, opening up a community garden, right? So these are different projects. They may have different costs, and there is a budget. So each project has a cost. So a special case of unit cost is sometimes called multi-winner voting for historic reasons. So if you have unit cost, right, so your budget tells you how many projects you can choose. If you have non-unit costs, so then sometimes maybe you select 7 projects, sometimes you select 9 projects based on costs, right? So the number is not fixed. And you have a set of voters, and voters have preferences over project, which they may express by some ballot format. So typically approval ballots, but often also other ballot formats. Right, so for the purpose of the talk, I'll focus on approval ballots, but kind of the way you can extract preferences from approval ballots is not straightforward. So the goal is then to select a set of projects that is feasible, that fits within the budget B, and to do that based on voters' preferences. So this isn't just a nice to have thing, like a thought experiment that would be nice to allocate funding in this way. Participatory budgeting actually happens around the world. So it started in Brazil, in Porto Alegre, in 1989, right? And now, since then, it's spread around many parts of the world, right? So it certainly remains very popular in many municipalities in Brazil, but also in Europe and North America, right? So for instance, in Paris, I have the number here for 2023, 75 million was spent on participatory budgeting projects. Evanston, which is where Northwestern is based, it's a much smaller scale, but also Evanston is much smaller than Paris. $3 million were spent based on public vote. Right, Cambridge, Massachusetts, so another US town, roughly the same size as Evanston, 2 million. Yeah. Okay. And in Scotland, legally, 1% of local government budget has to be spent on participatory budgeting projects, right? And to emphasize, okay, so this is not how you fund schools or fix potholes, right? So these are typically nice to have projects, so people decide which of these they found more important and more desirable. So how do people express their preferences? So in the theoretical part of the work, we'll focus most on approval ballots, but in practice, again, there's a wide variety of what is being used. So there's something that's called knapsack ballots, where people say, okay, this is if it was up to me, this is how I would spend the money. So this isn't very good because you don't get to express equivalences between projects. Like, I'm happy with that park proposal, right? I want to select one of them, but I'm basically equally happy with the other, right? So with knapsack ballots, you don't get to express that. You can have approval ballots where you say which projects you like, which projects you don't like. K approval is when you're allowed to specify exactly K or at most K. You could have cumulative when you distribute points over projects. You could have rankings, right? So the various ballot languages will focus for the theoretical analysis and approval ballots. So given these ballots, how is project selection typically decided? So most frequently, it operates by greedy. So greedy means that we order the projects either by number of votes or by number of votes per cost. So we want projects that get a lot of votes and that cost less, right? We order them in this way greedily, right? And then we go through the list of projects one by one, selecting and we stop if we are about to exceed the budget, right? So there are two flavors of that. Either you stop immediately when you're about to exceed the budget, or you check maybe there's something further down the line that is still affordable, maybe doesn't have such a good, number of votes or votes per cost ratio, but still fits within the budget so you can jump over, right? But the initial ordering is greedy. Okay, so to illustrate, so Cambridge 2024, so this is the kind of project that got funded, right? So the projects that are infrastructure projects, like shaded seats on hot streets, upgrade of public toilets. The projects that are supplies for unhoused residents, so like one-off spending, right? But this is the flavor of things that get funded. So voter turnout is relatively small, so they went slightly over budget, so that was apparently allowed. So the voter turnout was 10,000 out of 120,000, so voter turnout is a big issue with participatory budgeting in general, right? And so they did this greedy thing that is by the number of votes. Okay, so what do we want in participatory budgeting? So assume that voters actually have approval preference of the project. So they like some and there are others that they don't care about. So what is a good way of allocating the money? You can say that we may want to maximize the utilitarian welfare, right? So we may want to maximize the sum of voters' utilities, where you get, say, 1 unit of utility from each project you approve if it's selected, right? And you may want to maximize the sum of that over all voters. So the problem with that is that you may be in the following situation. You've got two parts of town. One is north of the river, the other one is south of the river, right? And they're almost equal size, but one is slightly bigger. And the residents of each part of town approve 3 projects, each costs 1/3 of the budget, on their side of the river. And they don't approve things on the other side of the river because it's too far a trip, right? And if you go by votes or votes per cost, right, you're going to build 3 projects on one side of the river and 0 on the other side of the river, right? And that feels unfair and generally less than ideal. If you have these 2 parts of town that are nearly balanced, okay, so at least you should have 2, 1, maybe it's okay to put 2 where there's slightly more population, but it shouldn't be 3, 0. Right, so we want some form of fairness. How do you conceptualize fairness in this context? Well, a basic idea that comes from, I would say, recent work in computational social choice is that an appropriate notion of fairness in this context is that if you have a large group of voters with cohesive preferences, similar preferences to each other, then such groups should be represented in proportion to their size. Right, so for instance, here you have a cohesive group of voters on the smaller side of the river, right, and therefore you want them to be represented. You can't give them half of the budget with this preference structure, but at least you should be able to give them something. Okay. So I can talk a little, let me actually, yeah, so how do we think about voters' utilities? Right, I'm going to keep this brief because we don't have that much time, right, but if voters submit approval ballots, one natural way to think about the utilities is approval utilities. You get 1 from each project you approve, you get 0 otherwise. You can also think of it in terms of costs, right? So the intuition here is that if you approve a project that costs 10,000 versus a project that costs 100,000, right? So maybe if you approve them both, you actually get more utility from the more expensive project, because otherwise it wouldn't seem like good value for money, right? So there's something that's called cost utilities. When we say that for each project, a voter gets utility that is cost of that project if she likes it. Right, so we combine approval ballots, so the voters still submit approval ballots, but the way they derive utility, we assume that this is how much money is spent on them. Right, so there are downsides in making this assumption, right, but I mean, there are also upsides. It probably doesn't make sense to think that all projects of very different costs have exactly the same value to me if I approve them. So more generally, So I'm skipping one case, I'll come back to it. More general, you can imagine that voters report actual utilities for each project that they like. Right, and an intermediate option, so I'm skipping one here, let me come back to it. So the intermediate option here is that it's uniform utilities that approximates between the cost case, and the general case is when each project is associated with some utility which you assign to it if you actually approve to it and if it's selected. Right, and the difference, it's kind of like cost utility, but your utility for a project isn't necessarily the cost, it may be some other amount, like how good that project is if it's implemented. Right, so approval ballots, so the point here I think is that approval ballots don't necessarily mean approval utilities, right? So you can take approval ballots and derive utilities in other ways. Okay, so given that we have a definition of players' utility, so how should we talk about fairness? Well, the classic notion kind of that captures that, large cohesive groups of voters should be rewarded according to their preferences is what I was actually teaching in the respective mini course, right? So this is the notion of the core. Right, so it will be familiar to students who have been here today and yesterday. Right, so core stability in the context of participatory budgeting means the following. So core stability, as the students here know, requires kind of thinking of the situation as a coalitional game. Right, and the natural coalitional game here is to say that we have a budget B, we have n voters, so each voter should have a say over B over n kind of amount of money, one nth fraction of the budget. Right, and the associate coalitional game is you take any subset of voters, let them take that money and decide how to spend it. And it should be the case that our budget allocation is at least as good for each group compared to what they can do with their own money. Right, so in other words, we say that an outcome, a set of projects, is in the core if there is no group of voters that can use the money that they control to purchase an alternative subset of project so that each voter in the deviating group prefers the new set of projects to the old set of projects. Right, so no group of voters can deviate and build their own projects. So the core, I think, is a very appealing solution concept. But again, as the students in this room know, we don't necessarily have not all games have non-empty core. Right, for this specific game, the situation is difficult. We actually don't know. We don't know if the core is non-empty for approval utilities. We know it can be empty for general utilities, for approval utilities we don't know. Right, so it seems like a nice thing to aim for, right, but we don't know if the core is non-empty, we don't know how to build outcomes in the core. Yes?
When you say approval utilities,
so I get one unit of utility for each, yeah. So not for approval ballots, for approval utilities. The first. Yes. Mm-hmm. Right, and kind of further down the line, I think for costs we still don't know, and for general we know it can be empty. For costs, I'm not sure, maybe it's known to be empty by now, but for approval we certainly don't know. Okay, so you can handle that by considering approximate core, where you say that no group can deviate if the deviation shrinks your budget by fraction B. So note to students, this is different from epsilon core we talked about today in class, so this is different. Right, so this is kind of epsilon core that we talked about was an additive measure of approximation, so this is multiplicative. Right, so this is basically saying, okay, if a group wants to deviate, because then they're doing something improper, right, so their budget actually shrinks, and it shrinks by a factor of beta. Right, and of course, if beta is large, no one wants to deviate because this new project they will have to purchase, they'll have to purchase them with a shrunk budget. Right, so for large enough beta approximate core would be non-empty, right, and the game is then to figure out what is the smallest value of beta for which beta core is non-empty. Right, and it's known to be non-empty for beta at least 32, right, and I think it can be improved for some settings to 16, and from what I've heard, right, but this isn't entirely public, right, so there is work under submission now that gets it down to a single digit, right, but that is not public and I think hasn't even been verified, right, but anyway, right, so you can have approximate core, right, but we don't know what the best approximation ratio that can be achieved. So you can also take a different tag, right, and relax the notion of core stability in a different way. Right, so this is a concept, there's a concept, extended justified representation, that comes from multi-winner voting literature, right, and restricts how agents can deviate in a somewhat different way. Right, so in the notion of the core, a group can break off with their money, right, and this should be an improvement for every one of them relative to what they currently have. Extended justified representation is a very similar idea, but now the improvement should be uniform in a well-defined sense. So let me explain what I mean. So let me explain it for approval utilities. It can be defined for general utilities, but let me explain for approval. Right, so again, we say that each voter controls B over N, we say that an outcome provides extended justified representation, is stable in this weaker sense, if there is no group of voters that can deviate in the following manner. When they deviate, they should be able to jointly approve a set of projects Q, right? Afford in the sense that the budget they jointly control is at least the cost of the set of projects Q, right? And kind of if they deviate, it should be the case that the projects they now build are approved by all members of the group, right? And on the other hand, no voter in that group used to approve that many projects before. So it's an improvement for them, but it's a certain kind of improvement. Under core stability, I allow them to purchase a subset of projects where maybe I like 3 of the 5 projects, Rida likes 4 of those 5 projects. We may like different things, but for each of us, it's an improvement over the status quo. Here I say, whatever we build, we must all like every single project being built, and moreover, it has to be an improvement for each of us. Right? So this is kind of a more uniform notion of deviation. Right? So this is kind of restricts players in how they can deviate. So this gives us a hope that stability can be achieved. Right? And in fact, turns out that there is a voting crew that can guarantee this notion of stability. There is a voting crew that, for approval utilities, always produces an outcome that provides EJR. Right? And this is the method of equal shares, which I'm going to describe in the next slide. Even moreover, so there's an up to 1 version of EJR that it satisfies for general utilities, so it really provides very powerful guarantees. Right? And moreover, this method actually works in polynomial time. Right? So we can actually achieve a notion of fairness that is weaker than the core, but in the spirit of the core in polynomial time. Right? And this is more or less the only voting rule that is known to achieve that for participatory budgeting with approval utilities. Right, so what we do, so this is the equal shared method that appears in the title of my talk. Right, so let me explain to you that method. Right, and then in the rest of the talk, I'm going to explain why we are not entirely happy with this voting rule and what we do to explain it. Right, so this is the streamlining part. Okay, so what is method of equal shares? It kind of mirrors the definition of core and extended justified representation in that it distributes the budget to the voters, right, and then it tells voters to build coalitions so as to pay for projects. So again, each voter gets B over N dollars, right, and projects are added one by one. So how do we decide which project to add? For each project, it can be added if the set of voters who approve it can jointly afford it. So the rules of the game is that a set of voters who approve project B, need not be all voters who approve project B, maybe a subset, pool their money to pay the cost CP, and when they do that, they have to share the cost of P exactly equally. Well, with a small caveat, okay, so the cost needs to be split equally among those who pay for P, with the caveat is if someone is about to run out of money, right, so then instead of paying their fair equal share, they can contribute to the entire remaining budget, right? And then the other players have to pick up the rest of the tab. So if you're about to run out of money, you can contribute all your money, right? Even if it's less than your fair share, right? And players who still have money have to share the remaining costs equally, right? So for instance, if there's a project that costs 12, I only have $2 left, right? So Rida has 5, right? And kind of someone else has 5, right? So we can share it as 2, 5, 5, right? So that's accepted. Right, and it has to be the case. I can't just save my money and say, yeah, I don't feel like paying my equal share for, I'd rather pay a little bit less. So it has to be the case that I simply can't afford my equal share. Right, I pay everything I have. After that, I drop out of the game. Right, okay. And then, okay, so there may be many projects that can be afforded in this manner. So which one do we select at each stage? So the rules are we select the project that has the least maximum payment per voter. Right, and in a way, this is best bang for the buck. Right, so if you have a project of cost 12 that can be shared among 3 voters, right, and we have a project of cost 15 that can be shared among, 15, right, so we select the second one because in the second one the cost per voter would be 1, and in the first one the cost per voter would be 4, right, and if we have these, voters who underpay, right, so then the quantity we look at is not how much these guys pay, but how much the voters who pay the most for that project pay, right, so the ones who really have to pick up the rest of the budget. Okay, so let me show you, okay, and we do that, we select projects one by one for as long as we can afford them, and at some point voters will not be able to afford any new projects, and then we stop. So let me show you how it works. So say we have 4 voters, the total budget is 40, so the budget per voter is 10. Right, and we have projects with these costs. One costs 8, the other one is 21, the third one is 16. And we have voters with these approvals. So let me visualize my voters as rectangles that I'm going to fill with liquid according to what they purchase. So at the first stage, I'm choosing which project to purchase, A, B, or C. If I were to select A, its cost would be shared between two voters as 4 and 4, so the price per voter would be 4. In the second stage, I could share it as 7, for project B, its cost can be shared as 777, so price per voter would be 7, and for C, it would be 8. So which project offers me the best value for money? A. So I select A, right, and this is the end of the first stage, and now voters 1 and 2 only have $6 left. Okay, what do I do in the second stage? I have to select between B and C. How can I share the cost of B? The cost of B, ideally I would like to share it as 777. Voters 1 and 2 don't have 7. They can't afford to pay 7. So I tell them, okay, you pay whatever you can afford, so 6 per person. So what is left? 9. Voter 3 will have to pay 9. Right, and then price per voter of project B would be 9. Right, because there's someone who has to pay 9 for B. Okay, so what about C, right? And kind of these two voters, these two vessels are completely filled, right? And the third guy has to pay 9. Right, and the other option is we can try C, right? And C can be shared as 8-8 because voters who like C haven't spent any money yet. Right, and note that before stage 1, B seemed like better value for money than C, right? But now B seems like worse value for money, right? So therefore, in the second stage, we are going to pick C, and the outcome will be A and C. Okay. Is A, C good outcome? Well, it's debatable, right? You can argue that B, C would in fact be a better outcome. So B and C is affordable, right? And B is better for every voter than A, right? But this is kind of an artifact that we are doing it in greedy fashion, right? If we are doing things in greedy fashion, we expect some suboptimality anyway. And yeah, so in terms of this idea that we represent large cohesive groups of voters, you can see that favoring B over C, the reason we did it is because voters who favored C were less represented than voters who favored B. So given that A was selected, C was clearly a better choice than B, right? So this way we cover more voters, we achieve more representation for groups of voters, right? And that's kind of the intuition of what happens. Okay, MES is a great voting rule. It's polynomial-time computable because it's a great algorithm. It's even practical and can be explained to practitioners, right? And I'll explain why I'm saying that in a couple of minutes. It satisfies EJR for approval utilities, EJR up to 1 project for general utilities. Okay, can be explained. The reason I'm saying it can be explained is that it has been used in practice. There are 5 cities around the world for now, right, and some more that are negotiating it, that are actually using method of equal shares, right? So this is this is Velička in Poland. So this is Switzerland, again Poland, Switzerland, and I think Austria, right, or Netherlands. So we have Netherlands somewhere. Oh yeah, no, so this is Netherlands, and this is, I think, again, Switzerland. Right, so there are several European countries that several municipalities in Europe that are using it, and hopefully the number will increase, right? And basically, if you ask voters, if you show voters, this is the outcome of the standard greedy method, this is the outcome of method of equal shares, voters tend to like method of equal shares better, right? And they also seem to understand it quite well if you test them on the understanding of the rule, right? So this is in many ways an attractive rule for participatory budgeting. Right, so there's a beautiful website maintained by the inventors of this rule. So by the way, so I didn't give you the names. So the multi-winner version of the rule was invented by Dominic Peters and Piotr Skowron. The participatory budgeting is 2 of them, and Grzegorz Perczynski, a student of Piotr Skowron. Right, and they maintain this beautiful website, Equal Shares, which tells you both, has demos how to use the rule. You can take that website and explain the equal shared rule to your grandmother. Right, and I think there's a decent chance your grandmother would understand it. Okay. So, yes? I can come up and then I'll hear it.
Yeah, we can hear you. My question is, what are incentives properties of MES algorithm?
Okay, the question is, what are the incentives properties of MES? And I don't have good news for you, right? Okay. Basically, even for the case of multi-winner voting, right, it's very difficult to achieve basically truthfulness and proportionality like EJR, and much, much weaker than axioms than EJR are essentially incompatible, right? There are impossibility results along these lines. So basically what you want to do as a voter is you want to pretend that you don't like some of the project that you actually like, so that you don't have to spend on them and you can spend your money on something else that, you know, only you and a small group of voters like, right? So that you don't spend your money on the projects that will be funded regardless, right? And your money only goes to the projects where you are kind of marginally important, right? And there is no simple way around that. If you want proportionality, this is going to happen. Right, so the hope is that this happens that this type of voting happens in situations where voters are not particularly strategic, right? So this maybe isn't a huge issue, right? And of course, it's an interesting question to understand what actually happens in equilibrium if voters are trying to behave strategically, right? Whether some proportionality properties survive in equilibrium. So this is something that we don't understand at the moment. But yeah, so basically, yeah, it's not incentive compatible in any meaningful sense because of impossibility results. Okay, so, but yeah, in not being incentive compatible is not my biggest problem with method of equal shares. I do have issues with it, but it's not that. So my biggest issue with method of equal shares, and not just mine, but the authors of the voting rule, is that it tends to underspend. Right? Because if you think about it, you distribute the budget among people, then they go out and try to spend it, right? And what may happen then is each person is still stuck with some amount of money which hasn't been spent, so that's a budget unspent, but for every specific project, no one can afford it, right? People who support that specific project don't have enough money for it. And it turns out, okay, so formally, method of equal shares may stop and select a set of projects such that there is still a project that has some approvals, kind of, and is affordable overall, so the amount of budget left over is greater than the cost of that project, right? But method of equal shares can't purchase it, right? And this is a systematic problem. This actually happens typically, right? So this isn't an edge case. This is how method of equal shares usually operates. So the approach that was selected by the authors of the method is budget completion. Okay, so you can say, okay, why is this even a problem, right? Because nice properties of method of equal shares have been proved, right, even in case of underspending. As soon as method of equal shares stops, it selects a set of projects that satisfies EGR, right, even if it fails to spend the budget, right? And then you can spend that money in whatever way you like. Right, so the downside is you have to explain it to the voters. Right, so you can't tell the voters, okay, we used method of equal shares, we spent 30% of the budget, and the remaining 70% of the budget was spent on the pet project kind of the head of the committee. Right? So you have to do it in a somewhat systematic way. You can do it by utility, but then it also means you have to explain fundamentally two different rules to voters. First we do this, and then we do things by utility, right? And you get questions, why didn't you do it by utility in the first place? So things get complicated. So you kind of want to explain one voting rule to voters, and you want it to spend more money. So you do it by budget completion, right? So the idea is that if you give method of equal shares true budget, it's going to underspend it. So how about we pretend to give it more money? We give it a virtual budget, B prime. And if you give it that virtual budget, so the hope is it will spend more. It will underspend with respect to the virtual budget B prime, but it will spend more than it was paying with budget B, right? And hopefully, if you increase B prime just right, you'll get very close to the true budget B. You don't want to overshoot B. You don't want to spend more than B. B is your true hard budget, right? But you select B prime so as to spend as much of the true budget as possible. Right, so that's the intuition. What is done in practice is that we run method of equal shares, first with the true budget B, then we give each voter $1 extra, or it may be a Swiss franc or euro or zloty in Poland, right? And we rerun it and see what gets implemented. And we do that until we run out of the true budget B, right? And if we do that, we stop. Right, and we stop and we go back to the previous solution. Right, and hopefully by doing so, we'll spend a bigger fraction of the true budget. Okay, and so this is the actual procedure. It hasn't been formalized as an algorithmic problem, but if you ask me, there's an implicit algorithmic problem here. We're trying to find an optimal budget B prime so that method of equal shares, when run on B prime, spends less than B, but as much as possible. We are maximizing the spending, given the constraint that the spending still should not increase B, right? And we do that by playing with this virtual budget. Right? So this is the optimum budget problem. Do we know how? Okay. And what happens here is effectively a greedy approximation heuristic for the optimum budget. So what do we know about it? We don't know anything. Right? So we suspect it's NP hard, but we don't actually know. We we can show it's in NP, but even that is not completely trivial. So why is it not trivial that it's in NP? Because even if the budget is integer and all the costs are integer, the optimum budget may still be a fraction. And it may be a complicated fraction with kind of complicated numerator, complicated denominator, right? You need a delicate argument saying that these numbers don't get too complicated, that your optimal budget is still efficiently representable, which is what you need to show that this problem is in NP. Right, okay, so it's in NP, but in a non-obvious way. Right, and solving it, yeah, so we think it's NP hard, we don't know. Right, and what happens, what we do now is a heuristic for optimum budget. So why is it heuristic, not an optimal solution? Right, so in what way does it fail? It fails in a number of interesting ways. So first, the spending, you may have wondered if it's actually monotone in the amount of money you give. Can it be that you give the method more money, but it ends up paying less? Yes, it can happen. Right, so it may be the case that you give it more money and you end up spending less. So, yeah, so you have this non-integrality issue. So if you do the current approach, you only ever iterate through integer budgets. And maybe your optimal budget is non-integer, right? And if you do this, you miss that, right? So we can't rule this out, right? And certainly in our experiments, we found instances where interesting things happen at non-integer budgets. We haven't found one when the optimal solution is non-integer, but we found ones where something interesting happens in non-integer budgets. I'll explain that in a second. And of course, we don't know how many iterations we need. So we don't know where to stop, right? And it's kind of annoying because, you know, if you give each voter $1 extra, right, and all projects cost like on the order of $10,000, likely kind of it's not going to change anything, right? And then you do another iteration and nothing changes, right? And then eventually something changes and you continue to do that, right? And kind of you may have to do it for a very long time. You may need a lot of iterations. Okay, so how do we go about that? So optimum budget, yeah, so we spend some time thinking about it, right? So we kind of want to solve optimal budget, but we don't know how to do that. And in fact, perhaps we don't even necessarily want to do optimal budget because optimal budget would be hard to show to the voters, right? Because what you're going to do is you're going to say, okay, we actually have $2 million to spend, but we're going to run our algorithm with budget, you know, $3,258 something, some number of cents, right? And then we get some spending, right? And this is the best we can do. Okay, how do you justify this amount? Right, so what we want instead, perhaps we don't even want an algorithm for optimal budget. Right, so this iterative thing I think is appealing and intuitive, but we want to do these iterations in a less stupid way. We want to do iterations in a way that don't miss optimal solutions, and we don't want them, and we want not to have, you know, stupid iterations that don't change the outcome. We want an iterative version of optimum budget, right, but one that doesn't miss good solutions. Right? And because of non-monotonicity, we don't want to stop as soon as we exceed the budget. We actually want to continue all the way and explore all possible budgets. Right? So if we had like good algorithm for kind of iterating through budgets quickly, I think that's even better. We need that rather than just solving optimum budget. We need good iterative algorithm because this is what we want to show to the voters. Right? So there's a whole challenge here. What is a good theory of explainability for participatory budgeting? Right? But what I'm sort of trying to point to is that we want an explainable method, and I think opt budget is not explainable, but an iterative method would be explainable. Okay, so to give you an example showing that this underspending is a real challenge, so this is what happened in kind of in a small town in Poland. If you run the method of equal shares with the true budget, you spend a tiny fraction of the budget. You spend 8%. Right? Okay, so you try to increase the budget, right? And then the first thing that happens is you overshoot. You get to this point, right? And suddenly you're spending more than 100%, so you have to stop. And when you stop, you go back to spending, 8% of your budget, right? And then as you continue increasing the budget, it's not monotone, right? So then you drop to spending 60% of the budget, right? So you kind of want to go from this point to this point. The best you can do on this instance, you can't spend it all, but you can spend 60% of the budget. And if you do, if you stop early, you're going to stop here, and this is bad. Okay, and if you keep increasing dollar by dollar, you can't really afford to explore this whole space of potential budgets, right? So that also is a cause for concern. Okay. So what do we do? What's our contribution? Okay, so I already said that. So iterative approach is appealing, right? So we want to have a smart version of iterative approach. So how do we formalize it? So instead of solving opt budget, I want to solve a problem that I'm going to call next budget, right? So here I'm given an instance of my problem, right? And I'm given, suppose my current virtual budget is B prime, which is already bigger than my true budget B, but I'm still underspending, right? So I want to ask, what is the smallest next budget such that something is different, right? At this new budget B prime, something changes. Maybe the set of selected project changes, or I change who is paying for them, right? But this is kind of skipping over all the iterations where nothing happens, right? So I want to go from a current budget to the next interesting budget, then to the next interesting budget, and this way I'm going to go through all the interesting budgets, right, and compute what happens at these interesting budgets, right, and then I know what is the best I can do by using this method. So what is the complexity of next budget? Yeah, we don't know. Okay, so with inefficient, okay, so what happens if we could solve that, right? So this is my wish list. If we can have an algorithm for next budget, then we'll never miss an optimal solution because we never jump over solutions, right? So from current value B, we go to the next value of B where something changes, the next one, we'll go through all values of B that give us different solutions, right? So we are not going to miss an optimal solution. We'll converge in polynomial time if the number of these qualitatively distinct, interesting budgets is polynomial, which I expect to typically be the case. In the worst case, it's not. We have an example where it's in the worst case exponential, right? But typically I expect this to be the case, right? And we avoid redundant computation. When we increase budget by $1 and nothing happens, right? So what I really want, I don't even care so much about optimum budget, I care about next budget. Do we know how to solve next budget? No. Okay. So what can we do? So here, this is an observation that was kind of implicit in the literature, but in this paper, including some of our own work, but in this paper we actually made it explicit. So method of equal shares, remember it had this funny caveat that if you are underspending, okay, so if you're about to run out of money, you don't have to pay your equal share, right? You can pay less, right? You can contribute to all your remaining budget, right? And others will pick up the tab. So what about we get rid of this idea? So what about we say that we run method of equal shares, but we eliminate that caveat and say that the cost of each project has to be shared exactly equally. Let's call that exact equal shares ES. Turns out ES has all the same nice axiomatic properties as MES, standard MES. Right, so this trick with having voters spend the entire budget was necessary. Question?
So when you replace with exacts, can you explain again what changes in the...
Okay, so suppose you now have so you've been running method of equal shares for some time, you have $2 left, right, and there are two other voters who have $5. And there's a project of cost 12 that is available. On the method of equal shares, this project can be purchased. On the exact equal shares, no one is going to take your $2. Right, so this isn't allowed.
Everybody should have the budget.
Everybody, yeah. So whatever is purchased has to be shared exactly equally. Right, which, okay, kind of is appealing from the fairness perspective. If you're paying for something, you have to pay your equal share. Right, and axiomatically, it's as good as the old method. So, okay, why was it not proposed in the first place? Because kind of from, private conversations with Dominic, they realized that this works as well. Why did they define method of equal share the way they did? Well, they defined it because this obviously would suffer from even worse underspending, right? Like in the example I just gave, right, method of equal shares would actually purchase that project of cost 12, right, and not stop, right, where the exact equal shares may just stop, and if there is nothing else that can be selected, it will just not select anything and spend less, right? So potentially it could suffer from even worse underspending. Right, so here's a concrete example. So let's take two projects. One is very cheap, one is very expensive. First vote approves both. Second vote approves only the expensive one. Right, if we go with method of equal shares, right, and we go by kind of value per money. Oh, so we go with method of equal shares. Method of equal shares says, okay, first project is shared at $3 per voter. Second one, 48. We should select the first one. Okay, budget is 100. First one is selected. Method of equal shares can now say, okay, the first guy has 47, the second guy has 50, they can afford $96 project, so let's select that. Exact equal shares say, he has 47, right, so he can't afford to pay his fair share, which is 48, we're going to stop here. Right, so this is terrible, right, so both projects could have been selected, but we stopped early, right, and you can scale up this example. So this is an argument against exact equal shares, right, but this argument is no longer valid. Okay, so that's the argument. This argument is no longer valid. Okay, so first let me say what I just wanted to say. This argument is no longer valid if we do budget completion anyway. Right, so this is kind of running the method with correct budget, right? But if you actually allow for budget completion here, right, exact equal shares will still select both projects. Right, so this isn't really an argument against it. Right, and in fact, exact equal shares, counterintuitively, may sometimes spend more than method of equal shares even without budget completion. Right, so I have Okay, I don't have an awful lot of time, but let me show you an example, right? It's kind of a variation of the previous example. So we have now 3 projects. 2 are cheap, 1 is expensive, right? And we have a bunch of voters. The first voter approves P and Q, second Q and R, right? And the remaining voters approve R, right? So what happens now is kind of, one extra stage of the previous project. Let's say per voter budget is 4. We have got 10 voters, so each of them can afford, has budget 4. What will method of equal shares do? Well, the first project, okay, so what are the values for money here? So for project R, I have 9 people who like it, so its per voter value is 4, right? For project P, it's only liked by 1 person, but it only costs 2, right? And project Q is expensive. So method of equal shares will select P, right? And then, okay, so then we look at project, okay, then we look at project Q. Q can still be afforded as 2 and 3. Right, because voter 1 still has 2 units of money, voter 2 has 3. They're not sharing equally, but they can still afford it. What happens now? Now we're at an impasse, right? R cannot be shared, equally or non-equally. We just don't have enough money because we spend $5 out of 40, we are left with 35, and that project actually costs 36. We don't have money. What happens on the exact equal shares? The second stage is not going to happen, right? So the second stage is not going to happen because Q cannot be shared equally, right? And therefore, kind of because Q is skipped, right? We can actually purchase R, right? So it's not an obvious comparison, right? So sometimes exact equal shares can spend more than method of equal shares. Okay, so this is an artificial example, so you can say that this is kind of wishful thinking, right? And if you try to look at empirical data, then what happens is that in practice, exact equal shares spends less than method of equal shares. So we've got this plot where we plot the spending efficiency of method of equal shares versus exact equal shares, right? And the example like here never happens. On 0% of instances, exact equal shares overspends method of equal shares, right? And typically it spends less and sometimes they're equal. And you can see that the spending sort of tends to cluster around spending half of the budget, right? So this also illustrates that underspending is a true problem, right? But this is without budget completion. So you can ask, okay, so what happens with budget completion? Okay, and what is the reason that we care about ES? So it spends less, so that's the downside. The upside is that it's a simple algorithm, right? And because it's simpler, remember these problems, opt budget, next budget, that we didn't know how to solve for MES. So there's hope that we can at least try to solve them for exact equal shares. Because it's simpler, it's easier to keep track of the budgets, it's easier to do things, right? And it turns out that indeed this is something we can do. Right, so for exact equal shares, there's an easy proof that optimum budget is in NP. We still don't know if it's NP hard. We suspect it might be, but we don't know. Right, but what we can do, right, and this is the one we really care about, we have a polynomial time algorithm, in fact, a linear time algorithm for next budget. Right, so it holds, so remember I showed you the scale of utilities, right? So we had approval utilities, cost utilities, uniform utilities, general utilities. We can't quite do that for for general utilities, but we can do it for uniform utilities, so including cost utilities, including approval utilities. Right, so this is a fairly powerful algorithm, and it runs in linear time. And it allows us to iterate the budget efficiently. Kind of in the interest of time, okay, so it may need exponentially many iterations, so we're not completely out of the woods yet, right? So it doesn't solve optimum budget, right? I would be surprised if it did, because it still smells NP hard to me, right? But in typical case, kind of there won't be 2 to them iterations. There won't be 2 to them interesting budgets. Right? So in practice, we expect it to converge quickly. Okay, so I have an outline of the proof. Yes?
So now that you have all these interesting budgets, how do you select one of them?
So I iterate through all of them, and I select the one which allows me to spend the biggest fraction of the true budget. Right? So I want to look at kind of what is possible, and out of those, I select the maximum. From real-life elections. So the data in the previous slide was generated from real-life participatory budgeting collection. So there's a great collection online of participatory budgeting data, PayBolib, right? So we took the data from there. So this is not synthetic, this is real-life data. Okay, I hope that answers, but thanks. Okay, so the way we prove it is we reinterpret exact equal shares a notion of stability, right? So this is slightly funny. So we had our basic notion of stability, which was score. We had EGR, right? And ES was a voting rule. It wasn't a notion of stability. But it turns out that we can define the slightly weird notion of stability that is specifically, you don't want to think about it as a kind of desirable notion of what is a stable outcome. But we can design it in a way that is exactly tailored to coincide with our outcomes of exact equal shares. So the way it operates is we think about outcomes of participatory budgeting process, not just as a set of projects being selected, but also about like how much each voter pays for each project being selected. Right? So we have this sort of cost division scheme. Right? And you can ask under what conditions this cost division scheme is stable. Right? And we have a notion of stability that is slightly weird and that I'm going to skip over mostly, which says that, okay, a project is unstable if, okay, a cost division scheme is unstable if either there is a set of voters that kind of have leftover money and can afford a new project from the leftover money, or else we also allow voters to withdraw money from the project they're currently paying for but kind of don't get good value for money out of them, and we allow them to take that money and spend it on a new project. So they can deviate by pool the money from one of the projects they're contributing to, right, and pool it with other people like that, who maybe use their leftover budget, maybe use this money they pulled, right, and jointly purchase a new project. Right, and we can show that this notion of stability exactly corresponds to ES in the sense that any outcome that is stable in this sense is an outcome of exact equal share and vice versa. So some careful tie breaking goes into that, so we need lexicographic tie breaking to ensure uniqueness both kind of for ES and for stability, right, but this can be done. So we can reinterpret exact equal share as stability and we can't reinterpret MES in that fashion. Mm-hmm.
All of them will satisfy stability.
Okay, so what I'm saying, okay, so if I run exact equal shares on a fixed budget, it produces a unique outcome because I break all ties deterministically, right? And this outcome will be stable in this sense for a fixed budget, right? So now the budget is fixed, and it's a fixed virtual budget.
But the real method that you will use in practice is not the one where you
it will iterate through budgets, yeah. Mm-hmm. Yeah, so the stability is for a fixed budget.
This is true for the if I use the iteration, I don't use any iteration, just I compose an output with the budget I have.
Yeah, so this is a claim about a fixed budget, but it's actually useful for iterations, right? And let me get to that in the next slide, right? So, okay, so next budget is what we want, right? And the intuition is, so suppose we have an outcome that is stable for a given budget, right? And you start increasing the budget. What happens? Kind of, it doesn't change if a voter wants to withdraw their money from something they're contributing to or not, right? So that doesn't change. But what changes is that voters' leftover budgets go up. You give each voter extra $1, and they already had some leftover money, right? So now they have like an extra leftover budget, right? So you may destabilize an outcome that is currently stable by giving voters more money, right? And in this fashion, okay, so you want to kind of recompute. So you're asking, so what is the smallest subsidy that destabilizes a given solution? Right, and if you phrase it like that, right, you can also ask, okay, so what is the smallest subsidy that makes voters deviate towards a different project? Right, so you fix a project, you ask, so what is the smallest extra budget so that at that budget there is a deviation from the current solution? Right, and that will be the next interesting budget. Right, and it can be kind of formulated as a cost-sharing problem, which I think in the interest of time I'm going to skip because I want to get to the end of the talk. Right, but basically kind of, so there is like a nice iterative algorithm that allows us to solve that problem efficiently. Okay, so now let's look at the spending efficiency again. So let's fix a budget. Let's look at the optimal virtual budget. Right, so we don't know, kind of, if we take the optimal virtual budget for each method, we don't theoretically know which is going to spend more, right? And we can probably construct examples each way, right? But empirically, okay, so if we revisit our example, right? So on that example, at optimal budgets, okay, exact equal shares, if you give it a little bit more money, it catches up with method of equal shares, right? So hopefully extra budget will help ES catch up, right? And it turns out, okay, that this is indeed the case. Right, especially at least with cardinal utilities. So when you interpret utilities as approval utilities, we call that cardinal utilities. Right, so they get kind of, and if you do this clever thing with next budget for exact equal, okay, so here you don't do anything clever, right? So this isn't using our new results, right? You're just doing budget completion separately for exact equal share and method of equal shares. And then exact equal shares almost catches up to the method of equal shares, right? So at budget completion, they're not that different, and that's without any additional cleverness, right? So this is just an observation that, yeah, they don't lose all that much, right? And now we have this power of efficiently iterating through budgets for exact equal shares, and we know for sure that we are not going to miss a good solution, right? And for method of equal shares, we don't know how to do that. So what happens if we bring that in? Turns out that if we just bring it in straightforwardly, it doesn't do all that much first computation, so that was a disappointment, right? But it also suggests a very natural heuristic that when you do this next budget, you don't just look into arbitrary changes, you look into changes that actually, you ignore changes that simply change the number of people who pay for a given project. Right? If currently it was supported by 2 people, you give people more money and then the same project is paid for by 3 people, we ignore those. We only look at changes with a set of project changes, right? Which is kind of what we are interested in. Right? And then it turns out that we can go really, really quickly, right? So these are running times, right? So if we do it in this fashion, right, we need many fewer iterations, right? And we don't really miss any good solutions, right? And if there's a risk that we miss good solutions, we can use that as an add-on to the original method. So we can take our method of equal shares with its original kind of add $1 heuristic, right? And we can add this kind of variant of exact equal shares that kind of does optimal skipping, and we can run them concurrently, right? And if we do it in this way, we spend more, right? So we get closer to optimal spending, right? So so our running time doesn't become much higher. So it goes from 466 seconds to 478, right? And in terms of spending, we get to spend more. And what is important, we have a guarantee that we are not going to miss an optimal, we are not going to miss kind of a fractional solution, right? Because we are doing this next budget take, right? So we are gaining in confidence, right? So we are gaining in and then either we are gaining in computation time, right? Or we can lose a little bit in computation time and gain in quality, right? So the picture here is not as beautiful as I hoped when we started this project. I was hoping for the picture that, we switch from method of equal shares to exact equal shares, right? So we lose kind of in immediate spending, but we gain in computational efficiency, and thereby we managed to find better solutions. That didn't quite materialize, right? But what we managed to salvage is that, we have a very clever heuristic that kind of by itself, maybe spending a little bit less, but is super fast, right? So this is the third column in both pictures, right? So it does spend less, like 0.86 as opposed to 0.9, right? So it's less fraction of the total budget is spent. So that's a bad thing. We want to spend a higher fraction of the total budget, but it's extremely fast, right? So that by itself might be useful for experiments. That by itself may have value, right? And the other option we have is to run both algorithms concurrently and select the best solution, and added computational cost of that negligible, and we do get better solutions. Okay, so that's kind of the upshot, right? So empirically, if we do both, we actually improve. So what this picture is showing is that if we do standard method of equal shares versus exact equal shares with next budget skip, right? So for cardinal utilities, we already spend more. For cost utilities, we fail to spend more, right? So this by itself, our theoretical work by itself is already good for cardinal utilities. It's not so good for cost utilities, right? And if you combine two, you actually get the best of both worlds. So to conclude, so we identified, right, and this was, I think, something that was known to the authors of the original paper, but they didn't really make it public, right, and some people in the community were surprised, right? So we realized that simpler version of method of equal shares still has all the desirable theoretical properties, right? Both suffer from underspending, right, but it's kind of ambiguous what happens in the worst case, and empirically, without completion, the authors of method of equal share were correct to define it in this way, but with completion, it's kind of complicated. So we don't know what happens worst case, but empirically, the difference is small, right? And the exact equal shares has the advantage, the exact equal shares has the advantage that it allows for fast implementation that doesn't miss optimal solutions, and the combined algorithm performs better on real-life data. Right, so this gives us better understanding, and the interesting theoretical questions here about comparing these two algorithms in the worst case with completion that I'm currently working on with a student at Northwestern, right? And there's a possibility here, there's an intriguing possibility that with completion, worst case exact equal shares is not much worse than method of equal shares, where the converse may be true. Right, so maybe actually my bad example for method of equal shares versus exact equal shares is more robust than vice versa. That seems plausible. Okay, let me stop here. I'm happy to take questions.
Thank you.
optimal budget with MES. So you try to do your original budget and then percent, etc. And so in the end, you find the optimal budget. And I was wondering, so then you compute MES of this B prime, which is something below B. So for instance, you had $1,000 and you end up with MES of B prime equal to 900, let's say. Does MES of 900 equals to 900, or is it correct? If you do MES on the
No.
what
So
you spend in the end, do you? Is it
no, it won't. No. It's not stationary in that sense, right? So it would be spending it still because I mean generically you expect voters to be stuck with money, right? And any voter stuck with non-zero amount, right, is kind of it means money underspent, right? And that happens generically. Right? It's very, very hard to avoid that. Right? Basically, if you knew how to avoid that, you would be solving knapsack, right? And we are doing something greedy and imperative, and thereby we are not solving knapsack. Right? I think knapsack is kind of useful intuition for what's happening here.
There is a question. Could you remind us our different processes for ES and
Okay, so at the level of definition, so the two rules differ on whether they allow a voter who is about to run out of money to contribute kind of the entire remaining money, drop out of the process, but not contribute their fair share. Right, so basically the question, kind of the difference between method of equal shares and exact equal shares is what they do if there's a remaining project that costs 12 and 3 voters, out of which 1 still has $2 left and 2 have at least 5. Right, and method of equal shares would purchase it, right, and say that the cost per voter is 5, and exact equal shares would say that this project is simply unaffordable and cannot be purchased. Right, and this then propagates throughout the process, right, so the two methods may end up with different outcomes. Right, and kind of the algorithmic difference is that for exact equal shares, we know how to solve the next budget problem, and for method of equal shares, we don't, and it's entirely plausible that it's actually an NP-complete problem. Okay. Yes?
So one question is, you select, you start by taking each method iterate, and you select the projects where people spend less money. What happens if you take the max money? Because in that case, perhaps you are going to spend more budgets.
Right, but you're kind of selecting projects, okay. You will be selecting projects that are approved by very few people, right? So imagine all projects have actually the same cost, right? If you are going for minimum bang for the buck, right? You start with a project. If you have a project approved by 100 people who can, all projects cost $100, right? If you kind of under this method, if one project is approved by 100 people, so cost per voter is 1. Another project is approved by 1 voter, cost per voter is 100. You are going to favor the project approved by 1 voter. So you don't want to do that, right? Because you will be just selecting bad projects systematically.
Okay. So, but this method has some properties. So did you study
No, I can easily construct worst case examples where it will be a terrible outcome, right? I will have like reasonable kind of outcome that will be selected on a reasonable instance, then I'm going to blow up that instance by a factor of 100, right? And I add up a bunch of kind of dummy voters that approve 1 project each, and I will show that it will be the dummy project that's selected as opposed to the good projects.
Thank you. And a question, you said that voters, when it was used in practice, you did you have some feedback.
Yes.
So how is there formal studies to see if voters understood or if
Yes, so this has been done on Swiss data in RO formally. There are published papers about it. So I'm working with some of these people where we also try to inject some actual artificial intelligence, like using large language models to help voters make their decisions, right? But so there's been a bunch of questionnaires. So it was verified that voters understand how the rule works. They were asked to predict the outputs of the voters on output of the rule on artificial instances, right? So there's been some kind of common sense checking that they understand.
It's not simple at all.
It's not.
I'm surprised that
Yeah, no, so it took some training, right? So we can't guarantee that everyone who participated in the vote at municipal level understood, right? But if you take a group of 30 people and pay them something kind of to participate in your controlled experiment, it's something that is teachable.
I would be interested in having the
Yeah.
results of that.
Yeah, happy to share.
Okay, so we'll try to I have other questions, but we can discuss them
Right.
later. And thank you very much.
Yeah.
For the
Thanks for
presentation.
coming.